Briefly recap what we did last time, 2 minutes. So we defined surface operators, or let's call them coefficient defects. By saying that, so we define Z1, Z2 to be coordinates on R4. And here there's a defect located at Z2 equals 0. And if we define Z2 to be in polar coordinates, then the defect is defined by saying that as R goes to 0, it takes this particular form. So there was defined by a partition of n. So we would call this defect, label them by some discrete label, n1 to nm. And in addition, in the path integral, you would introduce a two-dimensional theta term. Like so. And so the defect is labeled by these discrete integers which partition n, where this is the n of SUN. And so it's also labeled by these parameters gamma I and eta I. Some continuous labels and these discrete labels. And I mentioned last time that there is a way to calculate the instant on partition function in the presence of this surface operator. Let's call it GW. And in the limit of vanishing omega deformation parameters, you recover the prepotential of the gauge theory and obtain something else. So this has a 4D interpretation and this has a 2D interpretation. So these are the instant on contributions. And what I didn't mention last time, I'll just declare it now, is that there is also a classical contribution, just like F had a classical contribution which went like half tau A square. On the Coulomb branch of this 4-dimensional theory, W classical has a very simple expression which depends on how the Coulomb waves are partitioned in this way. So you see this corresponds to this Levi subgroup I mentioned. This is the unbroken part of the gauge group at the location of the defect. And so this leads to a natural partition of the Coulomb waves as well. And so you choose some ordering, so up to some permutation action on the Coulomb waves. What you do is to just list the Coulomb waves in order and partition them. So you take n1 of these, n2 of these, and so on until you hit an. Okay? And the classical superpotential will be just this set. So it will be a n I minus 1 plus 1 up to a n I. No, it will be, yeah. So I'll just declare that these n1 plus n2 will be called R2 and so on. So let me say R1 is n1. So if I declare this, then this will be okay. So you just sum these in each set, which is of length n1 or n2 or and so on. And these TIs are exactly the combinations I introduced earlier. which was gamma I plus tau, no, eta I plus tau gamma I. So this is a similar one loop path that I won't write down, but just like the prepotential had a split F classical plus F one loop plus F instanton, so does this W on the Coulomb branch. This is just a classical bit, and this sort of respects the breaking of the gauge group at the defect. And the only thing that depends on is a particular ordering that you choose. So
is this term and that term connected by supersymmetric? I mean, is that term one of part of the same supermultiplet? Is that?
I don't know.
No, not.
No.
It's a vector, yeah.
I don't think so.
Okay.
Yeah.
Just so roughly, where did that come from? Where is appreciated?
Where does it come from? Well, once I do the alternate description of the surface operator in terms of the quiver gauge theory in 2D, this is just Fairtelly-Laplace term. This comes from the tau sigma term that I'll try to describe. Yeah, from the 4D point of view, it's not obvious that this is the right thing to do, but.
In that description, the theta term is a superpotential.
Well, this has both. This has eta as well. In some sense. But anyway, yeah. Okay, so what I want to do now is to remind you of the quiver I wrote down and then just describe the GLSM from scratch. Okay. So any questions or comments about this?
So let me ask you, if you put this defect, and now, once in the presence of this defect, there's no constraint on the Coulomb branch. There's no additional constraint. This defect doesn't cause the Coulomb branch to be lifted.
No.
So as much of the Coulomb branch.
Exactly. Yeah. Right. Okay. So what? No. Ti is equal to this. This is the same Ti I defined last time.
And the next bracket is what?
It's just a sum of the Coulomb waves in the nth set.
It's the U1 part of the Coulomb.
Exactly. It's just a trace in the.
So it's
like trace file.
term,
Yeah.
Which is what some, yeah.
That's true. Okay.
You're saying that's what this W instant of, sorry.
That's a classical bit. So just like the prepotential had a tau a square on the.
So the eta I, AI part can be understood as coming from what?
You see, but this A is really the, so you have to, I haven't given a two-dimensional meaning to the A's yet. So here, this is just trace of phi in the UNI subset of UN, where phi is the adjoint scalar and d equals 4. But I haven't given that two-dimensional meaning. I'll try to give it now.
But your entire Lagrangian is just the, trace the mu square plus this surface term.
Yeah.
Right? So it has to come from something over there. Just to orient.
Yeah, exactly. So this surface term by itself is not supersymmetric.
By itself, you mean?
Yes. So it has some supersymmetrization.
Good. So it could be that this gauge field and phi come together to say to complete. Okay, but I haven't been able to show that from scratch. No.
Oh,
Yeah.
nice.
But if you ask, I want a dimension, mass dimension 1. So this has mass dimension 1, like F has mass dimension 2 on the Coulomb branch, and it has to respect this UNI.
But the gauge field and phi are not in the same two-comma-two multiplet.
No.
So it cannot come from supersymmetry.
Yeah, that's a topological term. That's true.
But you're saying
And
the two-dimensional description, you're going to get it by
only
it
if
will be the same number, right? Or not?
I mean, I'm saying that
Or one will be like an F term, the other D term.
this is a superpotential, and it'll come together. So no, this will have both. I'll try to explain that. So this will have both. Yeah, that's a good point. Yeah, try to explain. So good. So this is the defect. So this is this. So what? So the goal now is to understand how to get this from the point of view of a coupled 2D 4D system. And I motivated the gauge theory of interest would be a sigma model on this space, this flagged manifold, and we will describe this theory using a gauged linear sigma model. Of this form. But before we specialize to a particular form, let's just try to understand these 2,2 gauge theories in 2D. Okay. Right. So this is just a dimensional reduction of n equals 1 in d equals 4. So I'm going to try and give a very brief review of superspace in the 2,2 language, but it's essentially the same discussion in n equals 1, d equals 4. So you want to describe this in terms of some x mu. Mu goes from 0 and 1, and pair of theta and theta bar. And this, you should think of this as coming from the theta alpha, theta bar, alpha dot in n equals 1 superspace and d equals 4. It's some linear combination of these will give me this, and some linear combination of these will give me this. And thetas have the property that they square to 0. And these plus minus refer to chirality under the Lorentz boost that you have. So for instance, if you take x0, x1, going like cosh gamma, such gamma, for some gamma, then these theta plus minuses, so go like e to the plus minus gamma over 2 theta plus minus. And the same thing with theta bar as well. So they're like light-like combinations. And the n equals 1 superalgebra also reduces, can be written in this 2,2 basis. So I won't be very sketchy. So the essential algebra of interest will be that the supercharges commute to h plus minus p. Okay. So like in usual superspace, you can define the corresponding supercovariant derivatives that commute with all the supercharges. And now you can define superfields that are killed by some of the d bars. But because the plus minus are sort of split this alpha index, you can now define two kinds of superfields in 2 dimensions. Usually you define d bar plus minus phi equals 0 is your usual chiral superfield. So what that means is that this contains within it a scalar and fermions and auxiliary fields and so on. So for instance, this has an expansion like so. Where so it depends on both y plus and y minus. So here these y's are killed by the d bar plus minuses. So I get these notations are.
So if you have a chiral field, the XLR symmetry is broken.
Yes.
The equation
The vector
left-hand
preserves.
side does not seem invariant.
Sorry?
The left hand side is not invariant and
Yeah.
not covariant at all.
So 1 plus 1, so yes. And then now, yes, that's true.
So you just cannot have XLR. Once I have a chiral field, XLR is gone out of the field.
Yeah, so if you define the interaction like that, yes. mean, if you take phi bar, then you're fine, right? But if you define something only depending on phi,
I'm saying even the defining equation for phi, right? This is the left hand side is not covariant under XLR.
Is that true?
You're saying the axial R symmetry, there are two R symmetries.
Yes, yes.
Those that act on the Q's and those that act on the Q bars.
Yes.
And this is singling out Q bars rather than Q's. And therefore,
So that's fine. That's chiral supersymmetric, right? It's bound to be charged under
One or the other, yeah. It's okay.
You can still preserve it if you take it off, make sure that the rank is there.
charge.
Yeah. Yeah. This will constrain the interactions that you can have, I guess. Yeah. Okay, so y's are killed by these, so any function of this will be invariant under this. So you can show that this is the most general form of the usual superfield. But now I can split, I can say that d bar plus on sigma is 0, but it's d minus sigma, which is 0. So it sort of exchanges theta minus and theta bar minus, essentially. So what you can show is that the solution to this again can be written like some sigma of y plus minus.
So what was sigma again, please?
It's some chiral, just like phi. It's some.
Oh,
It's a guy that is
yeah.
killed by that. So now it will be y tilde, and again I have theta plus because the first condition is unchanged times some lambda or minus. It's some notation. But now I have theta plus. Sorry, theta bar minus instead of. Oh, did I mess up something here? Yeah, I'm not worried about that. Yeah, plus, sorry. No, I'm just wondering if I made a mistake here. Let me write the x expansion, is probably better. Yeah, I won't write the x expansion for now. So all I wanted to say was that if you wrote the x expansion of this,
There's also a theta minus term.
there is theta minus term, yes. I don't know why I missed it here. There is the theta minus term, you're right. Excuse me. It's theta minus psi minus, thank you. Thanks. Times some f. Whereas here now I'll have a theta plus, some lambda plus. But now I'll have a theta bar minus. And then something that looks like theta plus some other auxiliary field. And this y tilde refers from this by some signs. It will be x plus minus. Okay.
Y tilde has the property that it's killed by.
D plus bar and D minus, essentially. Yeah. Okay. So what I wanted to say was that there are two different kinds of chiral superfields, and because it's split between theta into plus and minus, so your interaction terms can now take. So in n equals 1, d equals 4, you had a d term and an f term. But now you can have a d term, an f term, and an f tilde term.
So you can't do this in any higher dimension because that would be breaking your x.
Yeah.
You can't split up a spinner.
No.
Yeah,
Exactly.
because SO2 is one dimensional.
Exactly. Exactly. Right.
This can also be done in 6 dimensions?
I
Because
don't
the
know.
Weyl spinner is again self-conjugate, so you can use either the Weyl spinner or the conjugate.
Just like this, you mean? Yeah.
Just like here, you could replace minus with minus bar.
Yeah.
Minus for the Weyl spinner and this is the conjugate.
Let's see. So what you will have d. What will the equation be?
So you want gauge covariant derivatives, which are what?
Valued in spinners.
Yes.
a Weyl spinner. So there will be an index alpha.
Mm-hmm. And now here.
You can use alpha bar index.
Mm-hmm.
And what would the condition you'd impose be?
Phi equal to 0.
What
This, you said this.
This annihilates the chiral multiplet.
Which one?
So in one of the cases, the first one, and the other one, the next one. Right?
Is that?
That's just the usual. That's like chiral.
Yeah.
What was important here was that he took, what would have been one spinner.
Theta alpha became theta plus and theta minus.
So in 6 dimensions also you have 2 kinds of spinners.
Yes.
Both of them are self-conjugate.
Yes.
So you can just you can say that d bar of the first kind of spinner is acting on phi as 0, and the d bar of second kind of spinner acting on phi as 0.
No, but
Or you can replace d bar by d in one of the.
So sorry, you're saying there's d bar alpha and d bar alpha bar. Is it? You're both there. Is that the point?
So d bar alpha bar and d bar mu bar. Mu is the anti-chiral Weyl spinner.
Oh, and you say so there are 4 sets just like this.
You will have
You're saying.
d bar mu bar in the second one as well. Right?
Okay.
This exactly mirrors the 2 dimensions.
So alpha and mu differ.
In chiral.
Mm-hmm.
No, I have to understand. You have to put a whole Lorentz multiplet condition. You don't split up a Lorentz multiplet in your conditions.
I'm using a Weyl spinner, so it's a Lorentz covariant.
Fine. So then I wouldn't call it analogous. Because here, the 2 components of a particular spinner are
So
broken.
here plus and minus were different Weyl spinners, right?
Okay, yeah, I suppose.
Yeah, they were.
Same thing.
It is. Okay. Okay, so you can define scalar terms, D terms like so. You can define now the usual chiral, usual superpotential terms like so. So these are, so this is the usual superpotential. But now you can define, so this will be d theta plus d theta minus. But now you can define d square theta tilde, w tilde of sigma, where this guy is now d theta plus d theta bar minus. Okay, so this is called a twisted chiral superpotential, and it turns out to be important because, as I'm going to show, the vector multiplet in 2 dimensions can be written in terms of a twisted chiral multiplet. That's the main point. Okay, so now let me briefly, this was quick, but I hope it's reasonably familiar to most people. So this is very nicely explained in Witten's paper from '93 on phases of 2-dimensional gauge theories. Okay, so in this quiver of interest, these guys, so these correspond to bifundamental supermultiplets, and they are the usual kind, the usual superfields, chiral superfields, these guys. And I'm going to show these guys will be, the gauge fields will be in these twisted chiral multiplets. So I'm going to ignore these for now, the usual chiral multiplets. I'm going to try to explain why the 2D gauge fields can be written in terms of sigma. Again, I'm just going to state some results. So in the West-Zumino gauge, the real vector field that has the content of your vector multiplet looks as follows. So in the West-Zumino gauge, it starts off with the theta theta bar term. And now I've specifically written them in terms of 2-dimensional notation. So A0, A1 are the 2D gauge fields. And the first terms are exactly what you would write down. So you see this comes from the theta bar alpha, theta bar, beta dot kind of term from d equals 4. But now the A2 and A3 components, they become scalars from the point of view of 2 dimensions. So we'll combine them, these complex combinations, sigma and sigma bar. And so the theta plus theta bar minus guys will look like so, with some sign convention. And then there'll be higher derivative terms and so on. But so this is your usual gauge field term that you could that you would write down. But now I've split them into 2D gauge fields and 2D scalars. So the A mu breaks up into a 2D vector and a complex scalar. Okay? And now the point is that you can define the following superfield, where these are gauge covariant superderivatives. So it's like e to the v d plus e to the minus v essentially. So you define this superfield, and you can show that this guy is a twisted chiral field.
Meaning it's annihilated by d plus.
Exactly. Meaning that d bar plus sigma is d and d minus sigma is 0. Sorry? This is, oh, yes.
It's the same.
Yeah.
It's like the square of this.
Exactly. Yeah. Good. Okay, good. And the sigma superfield is an expansion which starts with the lowest component is just this guy, sigma, the A2, A3 combination. So it will go like something like this, exactly what I wrote down earlier. Yeah. You can forget about all the bars and so on, and just focus on the theta plus, theta bar minus kind of thing. And then you see what happens here. The theta plus, theta bar minus is determined in terms of the d auxiliary field of the vector multiplet. And the field strength, V01, is d0a1 minus d1a0. You can call it F01 if you wish, but it's the 2D gauge field, so I'm calling it V01. And higher terms which involve derivatives. So now that I have a twisted chiral field which encodes the matter content of the field content of the 2D vector multiplet, I can try to write down interaction terms for them. Okay, so the kinetic term is simply what you would expect. Sorry, V2x for theta, sigma bar sigma. Exactly as you would do for an ordinary chiral field. This is the kinetic term, and this reproduces the usual Yang-Mills, 2D Yang-Mills. Okay? But now, because of supersymmetry, all interactions must necessarily be of this form.
Everything here goes through Fredonic?
Yes, trace. Yes. Yeah. Okay, so good. Now let's see what kind of interaction terms one can write down. So the simplest thing one can try is just a linear term. So the simplest term, the simplest interaction is to try d square x d theta plus d theta bar minus yeah, so sorry, I erased it. So it should be, d square x, d square d theta tilde. Since the action is real, it will be plus complex conjugate. So I'm just going to write both of them here. So so what I will do is just write capital sigma times some complex coefficient. So it will be tau real. So some complex parameter times the sigma superfield, sigma. And let me just write that down. So you see, all that matters for the potential term is when this term hits, because everything else will be 0 by superspace integration. So dot 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 plus theta bar minus d minus I v01 plus complex conjugate. So this gives you a trivial 1 when you integrate it. up to some signs, don't care about. So what I get in the component Lagrangian is something that looks like tau r times d plus tau imaginary times v01. Okay? So this is identified. So tau now, which is tau real plus I tau imaginary, is interpreted as the complexified phi theta plus parameter of the two-dimensional theory. So my interaction term is just tau sigma, essentially. W tilde, so this is the simplest term I can write down, and this captures the phi theta plus term Rd plus theta by 2 pi times V01. Okay? But more generally, if I had a W present, so a general W plus compass conjugate would give me, as you can easily check, we will get something like dw by d sigma plus, so the real part of the first derivative times d, and then plus the imaginary part times f01. Okay, there's a tilde everywhere. Bar times v0. Okay, that's the interaction part. So the idea now is to show that all these, that on the Coulomb branch of the four-dimensional theory, I'm going to show that all these chiral multiplets are massive. The ordinary chiral multiplets are massive. And so I integrate them out. And what I get is an effective action for W of sigma. That supersymmetry ensures that if I'm just looking at the vacuum structure of the two-dimensional theory, that will be governed by an effective W tilde of sigma. And all I have to do is to find the massive vacuum is to extremize this. Okay.
So now, forgetting about the matter for a moment, suppose now you just put in the sigma bar sigma term.
But that's not of this type. Oh, well, okay, you are saying it is.
Yeah,
Yes, it is. It cannot. Well,
I get a d minus I v naught, the whole thing square from that, right? So something like that.
yeah, is that right?
Just the kinetic.
Well, I have to first do the other integration first before I can write an effective W somehow.
Not an effective W, but just I want to see what the dependence in the action after you integrate all the superfields is on d minus d and v.
Oh,
So does a d minus I v naught
should get.
0 I square, right?
Oh, you're saying just from this? Yes,
Yeah.
yes.
And so now if you complete the square, what do you get from here?
I don't know.
So that's not homomorphic.
Yeah.
He's just saying there's a d square term there, there's a term here and d here.
Suppose you have standard kinetic term, doesn't matter for homomorphic or not. I just want to see what kind of potential the superpotential contributes. I mean, it will be roughly del W by del sigma square.
1 square, yeah.
But
Well, yeah.
what's the deal with this V0I?
Well, so there, it's just there. It
Meaning, what is its role in life? Does it does it?
No, because the
sorry.
chiral number you would get the geometric description, right? Is that what you mean?
No. He just wants to know if I just had these two terms,
And then
nothing
complete
else,
square.
what do I get?
Yeah. I mean, roughly you should get del W by del sigma 1 square. And that's the kind of thing you get.
Yes, he would. Yes, he would, but because there's a theta term, you have
So what's that?
So the thing here would be that you are allowed to shift the theta terms by integers. And so that leads to a minor complication where your effective potential, if you want to minimize it, you can in principle add NIs to lower the energy.
So wait, is this saying that here in this analysis you're pretending that V0I is a fundamental field? I mean, if you just thought of sigma as a field by itself,
Yes.
then V0i is just some other.
Yes, that's true. Yeah.
It's just some other field. Then we wouldn't even break it up into real and imaginary. We would just think of it in complex language.
Yes.
Think of del W tilde by del sigma
Times D. Mm-hmm.
that D bar, let's say.
Okay.
And then we would get just del W by del sigma, the whole thing squared.
Yes, yes, yes.
So if we were naive, I think that's what we would get.
That's what you would get, yes.
But V0i is not quite a field by itself because it was the field strength of something more fundamental.
Yeah.
And how does that play in? How does that matter? This NI business?
Yes, I think you are allowed to add such a term without, I mean, you are, I mean, if you write in the full bosonic effective potential and try to minimize it, you can see that depending on what what matter content etc. you have, you can sometimes lower the potential by adding non-zero NI terms. That's the extent to which it will play a role. I'm not sure I'm answering the question. But
So one loop term would be something like sigma log sigma, right?
yeah, I haven't gotten there. Let me get there slowly.
But so that would give rise to some kind of term which has the field strength times log sigma.
Yes, it would. Yes.
So what dynamical consequences?
Let's go there.
That's kind of what you guys.
Yeah, I have an this is just the forms of the terms of Lagrangian. So now I want to describe another possible interaction term that I can write down that will have important consequences, which is these twisted.
Just one related question. What constraint, the fact that V0i is a field strength,
Mm-hmm.
in what way does that constrain? Compared to just a completely arbitrary real scalar. One constraint is that its integral, its zero mode is quantized
Okay.
in units of 2 pi.
Yes.
Is there any other constraint?
A constraint on what? Just one understand.
So V01,
Yeah.
if you just wrote sigma as a basic field, you would
Yes.
treat V01 as an elementary scalar. If you didn't think too much, V01 would just be the imaginary part of that.
Okay.
kind of F.
Yes.
Okay, but it's not quite that. It's the field strength of a gauge field.
Yes.
So that makes it a bit special. Means it's not completely arbitrary scalar.
Mm-hmm.
And I want to know what constraints you get from V01 being a field strength.
I think it's what I said here that
So its zero mode is
that W isn't sort of single valued in that sense. You are allowed to add integral multiples of sigma, for instance. So
Good.
W shifts to W theta plus n sigma is an allowed transformation.
So you're saying that one constraint obviously is that V01, its zero mode is periodic with periodicity 2 pi.
Exactly.
And there's no other constraint.
No.
So I should just think of it as a periodic scalar and then I'm happy.
Yes. V01. Yeah. I think maybe that's a good way to say it. Yeah. But yeah.
But it's only the zero mode that's periodic, right?
Yeah.
Sorry, I
Integral equals yeah.
quantized.
That's right.
Only the zero mode is quantized.
Yeah.
I see.
Integral V01 is integral. Yeah. Okay. So now I want to explain another interaction term.
Multiplying V01 should be thought of as a periodic scalar.
Sorry, multiplying.
V01 should be thought of as a periodic scalar because integral of V01 is not x. That's the thing that you said.
Yes.
And these are multiples 2 pi to that.
Mm-hmm.
I see.
That places constraint on the imaginary part of dw tilde by dc.
D sigma. Yeah. Yes. So the real part of dw by d sigma doesn't has no constraint. This guy has a constraint. Yeah, that's true.
Thank you.
Good. Okay. So the new constituent is this idea of twisted masses that was first done in 3 dimensions, and then it also works in 2 dimensions. And for that, I have to consider some hypers. So now I consider these matter multiplets. Let's say there are n of them. You can of course add usual masses of the type mq squared as a superpotential term. But now suppose I have an SUN flavor symmetry.
Chiral multiples?
Usual chiral multiples. So like the fields I had in the theory. Bifundamentals at most, yeah.
So when do you just call them chiral?
Sorry? Chirals, yeah. Usual chirals. Fine. Chirals.
That was hyperbolic pairs.
Yes, exactly. Thank you. Chiral superfields, ordinary chiral superfields, no?
No, I don't think that they were converged in direct forward. They just named him to 2D.
Just d bar plus minus phi equal to q equal to 0. 2D chiral superfields. And there's a n of them, there's a global SUN flavor symmetry. Then the usual trick is to first weakly gauge this flavor symmetry, and then you put a back. So again, so this will involve introducing some linear superfield V, and then you just give a background wave. So this will lead to again its corresponding twisted chiral scalar in the way that I described earlier. So you just put a background wave to the twisted chiral scalar in the multiplet. So essentially all I'm saying is the following, that suppose you had a term like so, d4 theta. Now what I want to do is to, so let me put the I index implicit. Now I want to weakly gauge it, so I would put that. Let's call it V flavor to distinguish from the other one. And then I want to, so V flavor will be such that in its superfield expansion, as I saw, I mean, as I showed you, there will be a term which looks like sigma flavor. So this is the twisted chiral scalar in the gauged flavor multiplet, and you set that to be some constant matrix. So if I have SUN or UN, it will be some n by n matrix, and I choose M to be diagonal. Okay, and so this, yeah.
Wait, at the moment, is there a gauge? Sorry, is
So
there
this-
a gauge group as well?
No, I'm just considering this theory, just n twisted, no gauge fields yet. It's the simplest one. Yeah, soon we'll consider both. So this will lead to a term in the bosonic potential of the form. So if you just expand this out, you can, so this is d4x, sorry, d square x, d4 theta. So if you expand V, the V squared term will have, there will be a plus complex conjugate as well. So it will lead to essentially Q dagger M sort of mod square, that vector. So this will lead to mod square kind of term.
Wait, so M1 is the common wave of sigma?
No, M1 to Mn. I just break it. So you see, this leads to a breaking of the flavor symmetry to U1 to the N. So I break the flavor symmetry completely, right, because of this. And that leads to a term like so. And now I can do this for each of the chirals. In fact, if each of these, so see, this is a UR1 times UR2 times URM minus 1 gauge theory. So there are fields here which are R by R1 by R1 matrices and so on, right? And so if sigma gets a wave, sigma 1 to sigma Ri in the ith gauge group, you see that this is exactly what is happening to these guys. If I have a bifundamental field, right, and instead of this flavor symmetry, the waves for the sigma is exactly giving your mass to the chiral field that connects the two gauge nodes. So let me try to make this precise. So I'm saying the same thing will be true of bifundamentals when sigma gets a wave. So let me sigma is not equal to 0.
So this is supersymmetric thing.
Yes.
It's because there was no superpotential for that weakly broken,
Yes.
weakly gauged field.
Yeah.
So you could just choose.
Exactly. So for the bifundamental fields, I can do the same thing, except the now I'll have d squared x, I'll have d4 theta, and now I'll have a trace, and now I'll have e to the minus v for the ith gauge groups. I'm considering the I plus 1.
So this is a way to break the flavor symmetric down to u1 to the power n and then supersymmetric.
Precisely.
Passes.
And now I'm considering the action for these multiplets connecting the ith and I plus first node. And you can see it will look like this. Q.
No, so now I've not understood. What was your, are you now working with a gauge field and a flavor symmetry?
I could, or I could just work with two gauge nodes where the sigmas are given a wave. Okay? And I'm giving sigmas a wave because if I write down the
You're giving sigmas of the actual gauge fields of
actual gauge fields of wave, because if I look at the potential energy, so my whole goal is to find the ground states of the theory. And so if I look at the potential energy, there will be a term that looks like this. And so one way to minimize this term is to just make sigma diagonal. So it could be that you miss some states if you're not in the diagonal, if you go off diagonal, but you can show that there are no extra states, that sigma diagonal sort of captures all the ground states of your theory.
I see. So you're giving sigma of E. You've got this now, this structure.
For each sigma, so I make each of these diagonal.
You make each of, sigma was complex field. The non-trivial thing is that sigma and sigma bar commute with each other.
Yeah.
Okay. And you give each of them a
Diagonal wave.
diagonal wave, and it's a diagonal meaning all equal or not?
No, completely different. Sigma 1, 2.
Yeah.
Yeah. Generic
It has
waves.
to be larger than the gauge number.
Yes. Yeah. At the moment, let's say it's large sigma, let's say. Yeah. Good. So now I have a, so the Lagrangian for a bifundamental field will look like so.
And once again, you're allowed to do this because there's no superpotential for the gauge multiplets.
That's right.
Otherwise, the superpotential would force the sigmas to be some particular values.
You cannot write the superpotential for the gauge field.
No, you can have a double tilde of sigma.
This is twisting.
That will be, so we will combine all of these together. So now, but right now what I'm saying is that this term is independent of all that.
Okay.
So I'm going to diagonalize this and then see what is effective W that I obtain by integrating all everything else. And then I'll find the minima or extrema after that.
Instead of saying that you are actually giving it away, what you are doing is integrating out these cubes, right? And then you are interested in getting
Yeah.
effective superpotential for sigmas.
Yeah, but I'm never going to consider off-diagonal modes in the gauge multiplet. That's the point I want to make. That somehow what I want to say is that if I want to count if I'm only interested in the ground states, none of those off-diagonal modes matter.
And also, the justification for integrating out this cubes was that wherever your vacuum is a bit away from the origin.
Yes.
That's why cubes have mass.
Yes.
So it's kind of a.
Well, I'm going to give it mass by doing this to this node. Right. So I externally I put, as soon as I give a twisted mass like so to this node, and now you can see why Coulomb waves are twisted masses, because the job of the twisted mass just breaks the UN, the SUN or UN flavor symmetry to U1 to the n minus 1, and that's exactly what the Coulomb waves do.
Sorry, where did that U effective come from in the way that you presented it?
It should come from the sigma bar sigma term,
But
the
that
trace sigma bar sigma.
it's not, that term is not quadratic.
So you say, yes, I must have integrated out the auxiliary fields
And
of
what
that
is
theory.
the other term? Or there's this term of course would be absent with U1.
Yes, but then it's only a single sigma, and
Yeah.
and fine, yeah. Just give us back to sigma, yeah.
So just in your way of presentation, roughly where does this come? Just very roughly, where does this come?
think it will.
You're saying it'll come out from integrating out?
Isn't this just f squared? I mean, if I, this is the a2, a3 squared term. If I write a mu as a0, 1, 2, 3, and this is just a2, a3 squared, trace f squared essentially.
Becomes f squared in 4 dimensions.
In d equals 4, I mean, yeah.
Right. But suppose I just wrote trace sigma sigma bar, and you had your expansion of your superfield the way you showed it to us.
Mm-hmm.
What's confusing me, and I'm being stupid.
Yeah, no, I'm sure you're not, but yeah.
Yeah.
We can debate that, yes.
But what's confusing me is that it looks completely quadratic.
Non-quadratic.
No, the term that you wrote looked completely quadratic.
Sigma bar, sigma term.
And now you're getting something non-quadratic out of this, which is in general not possible.
Yeah.
So there's some.
Let me.
Yeah.
I don't have the Lagrangian with me, so maybe I'm making a mistake.
Yeah.
But yeah, I mean the diagonalization of sigma sigma bar comes from a term like so. Okay.
So the waves have to be extremely large, right? Around infinity, because this is a d term.
I work with large Coulomb waves, I'm done, right? If I work with large AIs, which are the large twisted masses for this node, that sets the scale for me. That's my mass scale in the problem. The 4-dimensional Coulomb waves set the scale for me. And I'm always working semi-classically there. So all AIs are large.
And the sigma is also have to be large.
So you have to extremize sigma and see what it looks like. And you will see that sigma will go like AI in the leading term. So then it will be self-consistent. And AIs are all generic. So sigmas will not coincide. So you ensure that if you choose generic 4D waves here, you have large twisted masses from this 2D point of view, and then you're fine.
So, one question.
Yeah.
The origin of this sigma field in the vector multiplet was the 2-3 component of the gauge field, right?
Yes.
It's
Yes.
4 dimensions. So it would be, I mean, if you were to turn on the wave for sigma, it would be the wave for 2-3 component of the gauge field. But now you're seeing the Coulomb, which is the wave for the scalar in the.
No, this is a different 4D theory from this 4D theory. I just want to say this for the point of view of this 2D node. As well, it's got nothing to do with this 4D gauge theory.
No, so this n,
Mm-hmm.
when you want to turn on the background value for the sigma field for the gauge field that is gauging this SUN symmetric.
That's this VF, yes.
Right?
Yeah.
So you are saying that is going to be the 4-dimensional gauge field, right?
Yes. Yes.
So
At the moment, it's classical. I will tell you how to make it quantum.
4-dimensional gauge group, in the 4-dimensional gauge group, the sigma field from the 2D point of view is the.
No, but I'm never making this node 2D. This is always flavor as far as this is concerned. I'm never making this into a 2D node.
What is the 2D coupling? I mean, the coupling of course happens in 2 directions.
I'll try to tell you what so this is the case I discussed here. If I have a node like this, so this could be n if you wish. Right? Then what happens is that what happens? So
Should I think of these sigmas as sigmas in the actual gauge fields or in some fictitious thing?
which one? Which sigmas?
The sigmas that have a wave,
The actual 2D gauge fields.
actual 2D gauge fields.
Yeah.
So with rank R1, R2.
Exactly. So if you write this, so you see for these guys now, it will be sigma I here, and for these guys it will be sigma I plus 1. Okay, and so if you do this carefully and keep the first and second order terms in vi square and so on. So you see, so vi is like theta plus theta bar minus sigma I plus complex conjugate, and vi square will be theta plus theta, let's see, theta square theta bar square times sigma I square essentially. Okay, so if you trust me, if you do this carefully and just look at the non-derivative terms, what you'll find is the following. So I get S going from 1 to Ri, T going from 1 to Ri plus 1. So my field is bifundamental. Okay. And what you get is sigma S. Let me write this properly. Small space. I get mod QST sigma S minus sigma T squared. So every bifundamental field in that matrix gets a mass proportional to sigma S of I and sigma I plus 1 T. Okay.
So it's this difference that's replacing just this plain sigma.
Exactly. And so if I had the last node, all that will happen is that for these guys, I'll just get QS I sigma S for the m minus 1th guy minus AI. Because now I see that the AIs that break the SU1 gate symmetry to U1 to the minus 1 are precisely what plays the role of twisted masses here.
Do they?
Yes.
Because I thought that the sigmas were the components of the gauge field.
Here, yes.
No, coming from the 4D, when you think of the sigma field, I mean the vector field as coming from the 4D, as you had explained, you had A01 and
Yeah.
A23.
Yeah, but this is just a purely flavor node. It has no dynamics. It just has these UN broken to U1 to the n minus 1 and this SU1 broken to U1 to the n minus 1 by such a guy. It's a purely 2D description of the Coulomb waves. Just as the twisted masses broke the flavor symmetry to its cartan, it's exactly what the
So you are gauging this SUN symmetry using the 4-dimensional gauge symmetry, right? You are gauging the SUN
yeah. This is a 4D node, but at the moment it has no dynamics. It's just SU. So these guys have some chiral symmetry under this.
Let's talk, if you look at the vector field coupling to that flavor symmetry in 2 dimensions.
Yes, this guy. This will be A's here.
What is that vector field? Let's talk about the minimal coupling, the coupling with the gauge field.
Coupling with the.
Gauge field.
The 4D gauge.
But there is no 4D gauge field at the moment. I'll tell you how to introduce the 4D dynamics separately.
So what is the gauge field in this multiplet?
There isn't. It's just AI at the moment. At the moment, it's just AI.
It's not turned on. The
I'll-
background field is not turned on.
I will tell you a prescription to turn it down.
No, but what is AI? I'm asking.
He wants to know if it's a 4D gauge.
Reduced to
Yeah.
2 dimensions. That's certainly. Yeah, because this is the wave of the joint scalar in the.
Right. So what I'm asking is, what is that gauge field in the dot dot?
It'll be some 2D gauge field that I'm not turning on at the moment.
At this moment, the 4D dynamics is completely frozen, so there is no gauge field from the 4 dimensions.
Yeah.
Is there some fictitious gauge field that we introduce?
But how are they talking to each other?
At the moment, it's just as twisted masses. The classical Coulomb waves are acting like twisted masses for the 2D
We
set.
don't know that the AIs are Coulomb waves.
No, you could put them MIs, no problem.
There is just
Some flavor. And I'll tell you exactly how to do it. So
So how does this 2, 2 supersymmetry embed into n equals to 2 in 4 dimensions? That will answer Abhijit's question.
No, yeah, I mean, he explained that already, right?
Yeah.
The vector field that
you
vector field
you
that-
write V as theta plus theta plus
That
plus.
cannot be A,
Yeah,
right?
so
It
that's
has
what
to be.
he's saying that you're explaining, that's why he's saying that.
Yeah, but I will not do it this way.
Embedding might be something more non-trivial than this. This was dimensional reduction, right? Maybe
Reduction.
embedding induced by surface defect might be more non-trivial.
It will be more complicated. I'll tell you how to do that. So at the moment, what I've shown is that I've figured out what the masses are for each chiral that I'm integrating out. Just sigma I minus sigma I plus 1 and sigma n minus 1 minus AI. And now the only question that I won't have time to explain, but I'll just say the result, is what is the effective action?
Wait, and you put a single chiral multiplet in the bifundamental between each node?
No, R1, R2 matrix, right? It will be, yeah, but yes, 1. Yeah, 1. Yes, yeah, that's right. So now, given all this, I hope you won't ask me how this comes about. I want to get somewhere else. So good. So the claim now is the following. This is the only thing left to write down. What I want to do is to write down the effective action for these diagonal fields, sigma is, obtained by integrating out each of these arrows. And the claim is that if the mass of the field is, so claim, the effective action is m log m by b minus 1. The mu is some UV scale.
Where m is the sigma minus.
Exactly. So when you integrate it out, it will depend on sigma, and so it gives you an effective action for sigma. So this is sort of the one loop effective action for sigma.
In this case, it will be sigma minus sigma.
Sigma I minus sigma I plus 1 and so on, right. So if you accept this, and this was first shown by the roommate of one of my collaborators in Italy, office mate, Dada et al. And actually there's a very nice one-page appendix by Cecotti and Watha that explains this from a superfield point of view. And also Witten's paper has an argument for just the one loop effective action. Yeah. Anyway. So given this claim and those masses, it's very easy to write down W of sigma. I'm going to get, I'll introduce a 2 pi I tau for, because, so for each node, I'll have the Fi term, right? I'll have summation I equals 1 to m tau I times, sigma is just the linear term. This is super field, but I'm putting small sigma because I'm tired of writing capital sigma.
So there are no quantum corrections to W effective sigma is.
Apart from this, no.
The one which is written in terms of sigma is.
And
That was a classical contribution till now, right? And
yes.
you need to incorporate one loop contributions and non-perturbative ones.
I'm doing it right now. So I'm saying the only contribution will be the one loop effective action. And the one loop effective action is going to be plus. And this is going to be messed around, but I think it should be clear what I'm doing. So for the first m minus 2 nodes, right, I'll have, so let me call this function omega bar, standard convention. So this will become omega bar sigma is minus sigma I plus 1t. Right, because that's the mass that we saw, and I'm summing over all s and t. S goes from 1 to ri, t goes from 1 to that is 1. And the last term will be I equals 1 to n, s going from 1 to rn minus 1, omega bar of sigma n minus 1s minus ai. And now comes Gaeto, Gukov, and Seiberg and says the following, that the way to turn on the 4D coupling is to write the last term.
No, so I meant one loop in the two-dimensional theory.
Punchline was coming. Sorry, what?
One loop in the two-dimensional theory.
Yes.
Are there such contributions? This was a classical case in the two-dimensional theory, right?
This one.
Yes.
And now I'm saying that for every field you integrate out, I get an effective action that looks like this.
But before integrating it out, I need to incorporate all sorts of corrections to this effective superpotential. Quantum corrections to this effective superpotential.
So the claim is the quantum corrections just come from here. This is it. Yeah, the claim is that if I just look at, if I want to look at the massive states of my theory, this is all I need to do. I'm just looking at some very basic questions. Maybe that's the point. I'm not looking at any dynamics. I just want to understand what are the ground states of the theory.
So in 4 dimensions, usually the classical superpotential gets quantum corrections. I'm not familiar with 2 dimensions, but this seems, I would expect that there will be quantum corrections just in 2 dimensions as well.
This is the quantum corrections. This is the 2D effective action obtained by integrating out the 2D chirals. There are these arrows.
But what about the starting function? You started with some function of sigmas. That should also include some quantum corrections, and then I integrate out sigmas, right?
Yeah, but the claim is this is it. As far as the vacuum are concerned, this is enough.
He's talking about this non-trivial interaction of the gauge fields.
Yeah, so I'm neglecting all that. I'm saying, I'm just, yeah, good, thank you. So maybe it's for the confusion. The off-diagonal modes of the vector multiplets are ignored at the moment. Sigmas are just sigma 1 to Ri.
So the only loop corrections you get is by integrating out the massive chirals.
That's the claim. So now the claim of,
But coupled to this is some sort of a topological sector coming from the gauge fields, right?
topological sector coming from these fields.
There are gauge fields also.
Yes.
Left.
Yeah, so this Ni sigma term will always play a role, yes.
Not the sigma, just the gauge field.
I think the sigmas are chiral super.
Yeah, this is not boson, this is the twisted, so this is the effective
But this
twisted chiral. So this has gauge fields as well. This is the effective twisted chiral superpotential. So this is a full superfield. I'm just writing the small letters, that's all. So the claim of, don't interrupt me now. The claim of Gaitha, Gukov and Seiberg is that, so this is a very nice paper. Is that if I want to turn on quantum dynamics in the 4D theory, all I do is, so this trace, yeah, let me write it down first now. And here I'm summing over S again. So you see, I just made this into a quantum operator in the 4 dimensions. So this wave is in 4D. So when the dynamics are turned off, the wave just gives you AI. But otherwise, I get a chiral correlator on the Coulomb branch. The statement is that the way to turn on the quantum dynamics of the 4-dimensional theory is by promoting this to the adjoint scalar of the d equals 4. This is adjoint scalar of 4D n equals 2. And I'm treating this as a chiral correlator, like Wev. So if I expand this out, I'll have trace phi to the k.
And we replace this term by that.
Yeah,
Expectation.
that's the claim. And what we'll see is that this is exactly the modification one needs to match our results with localization. I mean, we've checked that this is the correct proposal if you want to reproduce the results from localization. So you see, these are calculated from localization.
The expectation value is a 2D expectation value?
No, this is a 4D expectation. So this web acts only on the phi. So you treat this whole thing as an operator in 4D. I'll try to explain how this works in just a second.
Just like, what is the, I haven't understood what this quantity is what?
It's what
the
replaces
answer to
this.
what question?
Is the answer to the question, how do I now turn on the 4D dynamics? If I turn on the 4D dynamics, how does the one loop effective action obtained by integrating out those chiral multiplets, how does that incorporate the 4D quantum effects?
So how is the 2-dimensional theory affected by being in a particular 4-dimensional?
Exactly.
That's
This theory, exactly. Yeah. Okay.
okay. And this is more sophisticated than just saying replace the phi's by the AIs?
Yes, it is. I'll tell you why. Yeah, it is. So if there are no quantum dynamics, it's just that. Wherever phi is AI, but yeah. Okay, and now once I have this, what I do is to find the extrema, and I do the exponentiation so that I'm insensitive to this shift of Ni that I mentioned earlier, to make it single valued. So the claim is that this gives you the massive 2D vacuum of your theory.
Can I ask a question?
Please.
So what is the rough argument of that group of cyber? It says that, I mean, this essentially incorporates the full coupling of the 4D theory.
Yeah. Yes.
So, and roughly looks like semi-classically that phi enters through the twisted masses. So what is the intuition behind that?
I don't know.
They say something?
Not that I They said it, I haven't understood it, but
No, I mean, it's interesting. I mean, pictorially, it's like you're thinking, you can think there are like the 2D theory, then some coupling term, and then 4D theory, you sort of like integrated out the 4D and it turns out into the coupling like this. But it's just pictorially, they never do anything like that. It just starts from 2D and just to say.
this is a proposal for the
Proposal
incoupling.
is completely, the way I understand it.
But it's not like how Abhijit was.
Yeah, so there is no gauge field.
No, they don't put,
No,
they don't.
not the ratio of any kind as far as I can see.
In particular, this AI will not be from the, so this AI is from the 4D scalar and not from the 2 and 3.
No, it's the 4D adjoint scalar, yeah.
That's what because I always thought that the coupling is, in the gauge field. You're saying this is the coupling term. This should be thought as a coupling.
This is the coupling term. So it's sort of,
This is the 2D integral, right? E to the.
This is the-
It's expectation value of that. It's
in the 4D theory.
an action, right?
Yeah, this is the W term, but this, you have to solve the 4D theory first.
It's considered as an action, right?
I'm saying that
E to some of this power.
I'm saying that this sigma S couples to all chiral correlators of the 4D theory.
When we compute that expectation value, sigma S is supposed to be thought of as some background.
Yeah, some auxiliaries there. Let me try to explain how this works in an example, maybe it will become clear. So let's take the simplest example, which is the U1, I just have 1 here and N here. So let me try to explain something and then I'll answer Shiral's question of why it's not the same as putting it inside.
The only argument they give is for the rest of the structure, why it should be there, like from the flat manifold and all, given what we want to obtain. But that particular choice of the method, I think that's just given like that, for the rest of the piece of the file.
Yeah. I mean, in yeah.
Supposed to be action of the 2D.
Right.
So the coupling is e to the I integral d to x of this.
So let's consider this theory. So it's very simple. So this is just 2 pi I tau sigma minus, and let's do the 2D case first. So it says that, right? And now, see, this comes with the scale mu automatically. So let me just write that scale mu down. And so this tau is defined as the scale mu. And now I can just change this scale mu to some mu prime. And you'll see that this leads to a, changing the scale leads to a running of the phi theta plus coupling. So if I change the mu to mu prime, I can write this as mu prime plus log mu prime over mu minus 1. And because I have SUN symmetry, this leads to tau mu minus n by 2 pi I log mu by mu prime plus, yes, minus summation I equals 1 to n. This is just for a simplicity, I'll mention in a second. So now I want to define a 2D scale. I define my 2D scale, strong coupling scale lambda 1, such that tau of lambda 1 is 0. So I choose my mu prime so that tau of lambda to be mu lambda 1, so this is 0. So this term goes away, and I'm just left with this, where this is replaced by lambda 1. Characteristic scale of the 2D problem. Now I find the extrema, and what I find is sigma minus AI product, because the sums turn into products. So this function is such that d sigma or dx of omega bar of x is log x. So when I exponentiate, I just get x essentially. So these are the extrema of your W. There are n solutions, and they are one-to-one correspondence with the Euler characteristic of Cpn minus 1. Should be n. So if you just count the ground states, you're fine. So you can see that you don't need any other off-diagonal sigmas to capture the vacuum dynamics, vacuum structure. Now let me do the same problem now with phi present. This coupling present. So what happens?
Again, maybe going back to the original question. What identifies these AIs as the Coulomb maybe?
Well, not right now.
It broke the SUN flavor symmetry. Exactly like
That's the only.
exact. So to twisted masses break flavor symmetry from SUN to U1 to the minus 1. So do Coulomb webs. So the SUN is a flavor symmetry for the 2D gauge field. Therefore, the Coulomb webs are twisted masses.
Yeah, but what we identified is what you're going to do now. I mean, now you're saying, I mean, for now it could be anything, but now you're saying, imagining that this concept and this is about
Yeah.
localization of phi, and then you get all the accounts.
When we computed the index of this,
Yeah,
when we computed the index of this thing, we just thought of this lever node and gauged it with the gauge field
Okay.
of the 4D.
Okay.
And that reproduced the correct index of it.
But the claim is that the proposal is that the way to gauge the 4D Fleming node is what I'm about to tell you. So
So you're saying the 4D coupling better involve a gauge field also, the 4D gauge field also?
it involves solving the 4D dynamics in terms of a Sybek-Witten curve and knowing what the chiral correlators are in the fully quantum 4D theory. Let me just do this and it will be clear. So the analog of this is now minus Web trace sigma minus phi log sigma minus phi by lambda 1 minus 1. Right? It's just this. It's that. Now I do this. What I get is the following. I get exponential of trace log, and this is the key. You can't take it inside. If I could take it inside, then I would get the same thing as product of sigma. But this is an object that has been much studied by Nekrasov and collaborators. So let's put lambda 1 here. Equals 1. And this is nothing but the resolvent of your gauge theory, 4D gauge theory. So the resolvent is traditionally defined to be, trace 1 by sigma minus phi. So what appears here is the integral of the resolvent with respect to sigma. And this has been solved. So this is the resolvent, 4D resolvent, which was solved by Cachaso, Douglas, Sybek, and Witten for pure SUN. And this has a closed form, which is given by as follows. So T of sigma looks like Pn prime of sigma by y, where y square is simply the Sybek-Witten curve. But this is 4D now. Okay, so the idea here is that all chiral correlators for correlation functions, you see, can be determined from this expression. Just expand for large sigma, both sides, and you can just read off. And the claim is that for n, for say trace phi to the k for k greater than n, is not determined purely in terms of the previous n minus 1. There are genuine quantum corrections. So this is like the 4D chiral ring, essentially. You can't take it from just, you can't treat it as a matrix. That's the point. So that's why it's not trivial taking it inside or outside. Okay, so if you know this, you can integrate this, and what we get is the following. And now we'll come to where surface operators make their appearance. So if I integrate that, what I get is Pn of sigma plus y over 2 lambda 1 to the n equals 1. So this is the exponential of dw by d sigma. And now if I, get rid of the square root there and so on, I can write the final equation. This is equivalent to the following form. Pn of sigma is lambda 1 to the n plus lambda 4d to the 2n over lambda 1 to the. So if I didn't have the 4D coupling, it's just what I wrote earlier. Product of sigma minus ai 1 to n is this, but now I have an extra term. And furthermore, this is the quantum corrected gauge polynomial. which means that I have to really write this as summation some sigma to the k u n minus k, but these are again calculated from the resolvent. It's not just a polynomials of, symmetric combinations of AIs, u n minus k. And so what is this? So let me call these new roots some sigma minus EI. And now you see that in the limit that these are all small, the n roots in terms of which I can do a small expansion. So I can write this as sigma equals EI plus, and so at leading order EI is just AI, so it looks like AI plus what? So if I expand about sigma equals AI, I'll get plus 1 by product I not equal to 1, A1 minus AI, times the same right hand side. Plus higher order terms. And these are this is telling you what the surface operator you're looking for. Because remember, this was for the theory 1n. So the surface operator is defined by a partition which is 1n minus 1. So you have to choose which A is singled out in your partition. So this will be the partition AI and all Aj not equal to I. So my claim is that if I did the original analysis of W localization with this partition in mind, I would get, so this is the solution to this guy. Now the idea is to put the sigma star back into W, effective, whatever it was here. I put it back into this, and I evaluate W of sigma on the solution. I would get back W localization. Okay.
What was the effect of this additional term? Just this additional piece that lambda 4 divided by lambda?
Yes. So at leading order, this is a term, but if you go to higher orders, they mix altogether because you have to solve it iteratively. At leading order, it's just like an addition, but there are more complicated terms at higher orders. So this reproduces the localization expansion, is what I'm trying to say. If I do W localization, this will be the classical piece, and this would be the Q expansion. What I wrote earlier was Q to the K to the 2 pi I T dot M, right? So in the massive case, this went to lambda to the 2n, and this would go to some lambda 1 scales. And this expansion is what I'm reproducing here, order by order. Okay, so the only thing I want to say more before I stop is, so what is the general vacuum about which I have to expand this?
Sorry, this expansion is expansion in terms of lambda 4 only.
But and also lambda 2. You see, there were other parameters here. So I'm saying those should be identified with the running phi, the strong coupling scales of the 2D theory. That's the claim. Right. So then.
For each vacuum, for each choice of vacuum, there is a
Surface operator. And now the question is, what is the choice of general vacuum that will give me, that will help me reproduce W localization for that operator? It's very easy actually. So if you just look at the ranks of these guys, so it's R1, R2, and so on. It's always increasing. So what we show is that the following works, where, so remember the original operator was A1 up to AR1, which was N1. It went to AR2. This had N2 terms, right? But you see, this has N1 plus N2 terms. So we did the most mindless thing possible. We said that AR1 will be the first guy, and that sits inside, this also helps with this idea of the flag manifold. This sits inside AR2, because the first AR1 will be here, and so on. So if we take this classical vacuum about, which first we can show that this is the solution of the classical equations, and then we show that solving the twisted chiral equations about this vacuum exactly reproduces the superpotential evaluated in that vacuum.
Yeah, theory is chosen to give finite gates.
Yeah.
The part that is unjustified is the one that you were everybody was asking about earlier. That's what the part is because if
And
you
sorry, so I want to say that if you now calculate what the classical W is, we had tau I times trace sigma. Then you can show that this is exactly, so in this vacuum, it exactly reproduces the W classical I wrote earlier, provided these phi 3 Laplace terms are related to our sums of tau j is what I call TIL, like something we show. So phi 3 Laplace terms are exactly these guys, and so when they run, they become these 2D scales that they map. Okay, so there are more things to say, but yeah, I think I'm out of time, so thank you.
Can you say the statement about the resolvent again? I mean,
Yes.
not the resolvent itself, the proposal.
The?
What did these guys say? Guko, Gaik, and Simon.
I can repeat it, yes. So, so the first point is that if I integrate out integrate out a chiral 2D chiral multiplied of mass m, I get a term like this, omega bar of m. First point. The second point is that if I have omega of sigma minus ai appearing, because in this case, for instance, I have only a single sigma and have n fields like that, then you want to promote this to an operator in the 4D theory. You want to interpret this as a vev of an operator in the d equals 4 theory. So I want to replace this by so this trace is in the n by n, in some sense. This trace in the phi basis. Sigma just goes along with the right as a. This is the replacement that they.
Trace W.
Yeah, thank you.
So a question that I think Abhijit asked earlier, but let me repeat it,
Mhm.
is in the 2D path integral, would this appear downstairs or upstairs in the exponential?
Because in one of the manipulations, somehow it was crucial that it appeared downstairs because he couldn't take exponential inside, right?
Upstairs, downstairs. What do you mean upstairs, downstairs?
E to the power, is it e to the power this, or is it just?
But I'm going to set it equal to 1. It makes no. I mean.
No, but I think
What's
in the effective action of the 2D theory,
Yeah.
this appears in the action, right?
Yeah.
In the twisted superpotential.
This is the effective twisted superpotential.
So in the path integral, it appears in the exponential.
Yeah. E to the s.
but that feels very unnatural.
Yeah, the way to write that this way.
Yeah, because I mean, you could imagine that you had some term like this, which was path integrated over both 2D and 4D. And then if you did the path integral over the 4D, that would give you expectation value of e to the power this.
Right.
Not e to the power expectation value of this.
And this particular thing will never appear in any calculation.
Right, why should?
Which particular thing?
This expectation value, the one that you wrote down.
No, but as I said, this is purely for the purposes of calculating the vacuum structure of the theory.
No, but since your expectation values are going to be different, expectation value of trace e to the power this,
Yes.
log of that,
Mm-hmm.
is not the same as e to the power.
Yes, it's not. This is the one that matches the localization calculation, of course. But so there's a strong check for this.
But doesn't it seem extremely unnatural that you take an expectation value upstairs?
No, because this is that so good. So this is an object that Microsoft defines in his paper with Peston, I think, right? E to the trace. Sorry, I keep pointing to you whenever I talk about Microsoft. I'm sorry. I should stop doing that. So this is an object that he says is more natural than vev of e to the trace log in some sense. So why was that? I'm trying to remember.
Because
It's this.
2D. No, I was just going to say that if this is the 2D superpotential, then it should just act as it just appear as a superpotential in the combined 2D 4D path integral, right?
It should, yeah.
So superpotentials appear in the action.
Yes.
Why would I ever need to take the expectation value of something that appears in the action?
No, it's the expression value in the 4D theory. I'm not touching the 2D theory at all. The 2D dynamics is still there, right? I'm not doing anything to it.
But if we think of this as a 4D path integral and a 2D path integral,
Yeah.
without any particular order,
Yes. So yes.
what is the operator that?
Yeah. Yeah. You're saying what is the interpretation of this object? So this is what this I forget this. This was I think the reference for this should be Nekrasov estimate. I have this is what he calls these Y observables, right? These are natural observables in the D equals 4 theory. I'm sorry I'm not able to give more, but
They don't have the web, right, in the Y observable. It's just the operator.
But anyway, so you're right. So this is the guy that appears when I write down the extrema, the equations for the extrema of W. This guy equals something, definitely.
So what happens if I die in two-dimensional gauge coupling?
What happens?
If I die, like if I change.
Good. So let me go back to this one. Let me go back to the localization calculation. Point is you can't. So if I get the Z instant on with surface operator, we saw this, right? Now if I do the localization calculations, you have m of these counting parameters, and if you just look at what f depends on, f should depend only on the 4D coupling. So the identification of the 4D coupling with these guys is that the product of everything is lambda 4D. Let's call it Q4D. So in this particular case, it's lambda 4D to the 2n. But you can't turn one off without turning off this as well. So you do first turn off the 4D coupling and then the others. There's a definite hierarchy here.
But this QI is the FI parameter?
Yes. This QI will be the, for instance,
What about the gauge coupling, the two-dimensional gauge coupling?
it's the same. Oh, gauge coupling, no, that's all gone. That's a 1 by E squared term that's relevant, and it's just, we only look at the superpotential term. Yeah, so what I wanted to say was that the QIs are identified with lambda i's to the appropriate, power that it's allowed to exist in, and then the product is the Q4D. So you can't turn off the 2D coupling without turning off, coupling, I mean the FI coupling without turning off the 4D coupling as well. There's a hierarchy.
So to just raise that question, so when we on this massive on the branch where these chirals are massive, the kinetic term for the gauge field is irrelevant.
Yeah.
So the only terms for the gauge field that arise are from integrating of the chiral.
Yeah.
Similar to this expanse story.
Yeah, I just want to mention that we've extended this to the case where I add an extra direction, S1. So you have 3D compacted on a circle inside 5D on a circle. And then it's much more interesting because you can turn on Chern-Simons level for both. And then you can again study how things depend on Chern-Simons levels. And the nice thing is that the 3D Chern-Simons level on a circle can also be written as an effective superpotential as trace sigma square. That's a nice thing that. It can all be incorporated in the same formalism. But the concept is the same.
Proposal did not involve omega background.
No.
Just for the 4D.
Yeah. Well, implicitly it does, because he says that in these polynomials P, the U's will appear, and they say you have to calculate that however way you want. One way is to use localization. As long as you know you can also use Savick-Witten, I suppose, yeah.
But if one naively follows what he said, you have a 4D gauge theory with a defect, so we naively just dimensionally reduce everything.
Yeah.
then would this be like integrating out all the continuous modes that arise from
I don't know.
This is the picture we had, right? But just a picture.
So the main dissatisfaction is why the wave appears in the exponent. Is that fair to say?
Yeah, I don't quite understand. Also, all the gauge coupling.
Gauge coupling.
Yeah.
Which gauge coupling?
I mean, I thought this n would be coupled to the four-dimensional gauge field. But
It is. You just have solved the theory on the Coulomb branch. This correlator knows all about the Fourier dynamics. It knows about the Savigilton curve because the resolver knows about the Savigilton curve. It knows about the instanton.
But from the point of view 2, 2 supersymmetry, which is broken, half compared to the starting point, which is n equal to 2, this find A are not related anymore.
Sorry.
The
From the-
4D Coulomb web
Yeah.
and the 4D gauge field are not related to each other anymore, right? So that
I mean, the gauge symmetry will act on the
it's
phi,
probably,
right?
yeah, I don't know. I mean, it will probably just my bias conception.
The 4D gauge field and the 4D adjoint scalar, he says. I don't understand why, because
when you
From the point of
mentioned
view
this
2, from the point of view 2, it's not.
They're different. N equals 1.
They're n equals 1, but
yeah. But I mean, but this chiral correlator was calculated in the D equals 4 theory,
No,
including everything. Right?
when you give all these sigmas waves,
Yeah.
aren't all gauge fields kinks?
To U1 to some,
No, I was thinking to nothing.
to nothing.
Because well, let's start with that guy. I give
Uh-huh.
the sigmas in the n a wave.
There is no sigma in N, is my point.
Okay.
It is never a 2D gauge field.
I give the A's. The A's are there.
A's are different, yes.
Okay. Now those were just fundamental under the last gauge group.
Yes.
So if you turn on every component into fundamental, that typically exists down the gauge field to nothing.
but what is the mechanism?
Just the 2D.
There are different buckets. You could also like a completely different description in which the sigmas are all set to 0 and
You get a geometry of CPN minus 1 or something like that.
That's actually the starting point for this, I think. That's where the definition comes from. That because of this idea that the Planck manifold that captures the data of the defect, and so you have that, but then you sort of like incorporate it into the GLSM, and then you use this other description on the Coulomb branch, in which all that geometric stuff goes away, is integrated out, and then you get this simpler sort of description in terms of the sigma that is not only intuitive, but it's workable.
Sorry,
Mhm.
your argument works if we give waves for the cubes, right?
Well, I was thinking
I
these.
will.
Yeah, so you can do that.
You can do that as well, yeah. Then you get the CPN model, the geometric mod q squared equals R.
Here we are on some other branch.
Another branch, yeah.
Like the Q's are massive, so they are.
They integrated out, and then you work with the sigma fields, yeah.
Just the sigmas.
Yeah.
Which are adjoints under each of these U's, right?
Oh
Yeah, yeah,
So
yeah,
there is just
yeah.
And those in the vacuum you're dealing with, those guys don't have waves because those were all
No,
massive.
yeah, exactly. They're all massive.
Okay.
Thank you.